Hello friends, welcome to Engineering Funda family. In this video, I'm going to explain you hybrid Pi model of BJT. See, hybrid Pi model of BJT that we use for high frequency AC analysis of BJT. For low frequency AC analysis of BJT, we use hybrid model and RE model. So hybrid model and RE model that I have already covered in my video lecture series of basic electronics. In this video, I'll explain you hybrid Pi model in great details. So I request you to see this video till last. All the basic fundamentals that I'm going to cover in this video based on hybrid Pi model of BJT. So let us discuss basics of hybrid Pi model first. See, hybrid Pi model is an equivalent model of transistor. So instead of transistor, we will be representing equivalent circuit based on hybrid Pi model over here. See, hybrid Pi model is widely used after hybrid model and RE model of transistor. So initially, people were doing AC analysis with the use of RE model and hybrid model. Later, they came up with the solution with the use of hybrid Pi model. See, hybrid Pi model gives better clarity compared to RE model and hybrid model. Right. See, in hybrid model, parameters are generally defined for any operating conditions. So in my earlier videos, I have defined all the parameters of hybrid model. You see, here you can observe this is hybrid model. So in this hybrid model, parameters like HIE, HRC, HFC, HOE, so all these parameters that has been defined for general operating conditions, right? And see, I have already explained RE model even. So in RE model, parameters are defined by actual operating conditions. So I have told you during RE model that RE model is better compared to hybrid model, right? See, in RE model, parameters are defined by actual operating conditions. You see, in my last video, I have explained RE model. This is the RE model for common emitter configuration. So in this RE model, I have defined parameters like RD, then RO, then this current source beta IB, right? So these are the parameters that is based on actual operating conditions, right? But one should know, see this H model and RE model that we use it with low frequency AC analysis. Hybrid Pi model that is used with high frequency AC analysis. See, hybrid Pi model can also be used with low frequency AC analysis with some modifications in hybrid frequency model. So in this video, I'll cover high frequency hybrid Pi model as well as low frequency hybrid Pi model. So first, I'll explain you high frequency hybrid Pi model. After that, I'll explain you modifications required for low frequency hybrid Pi model, right? So here you can observe we have hybrid Pi model for common emitter configuration. So here you can observe this is transistor where this emitter terminal that is common with input and output, right? That's why this is common emitter transistor, and this is equivalent hybrid Pi model of this common emitter transistor, right? Where you see input voltage is VBE. Here you can observe input voltage is VBE. Here output voltage is VCE. You can observe output voltage is VCE over here. Input current is IB. Here output current is IC, right? That is how equivalent model that is there with us in terms of hybrid Pi model for common emitter configuration, right? Now I'm going to explain you each and every parameters of this hybrid Pi model first, right? So here, see, you can observe we have two capacitors over here, Cu and Cpi. This Cu capacitor that is used to represent effect of early effect, and it is there in terms of few picofarad. See this Cu capacitance, that is a capacitance in between base collector terminal. Here we have base terminal, here we have collector terminal, right? So this Cu capacitance, that is a capacitance in between base collector terminal, and this capacitance is explaining you effect of early effect. If you want to understand early effect, then you just go through my video which is available in electronic devices and circuit. I have explained early effect in great detail. To represent early effect, we have Cu capacitance over here, right? This C-Pi capacitor, that is diffusion capacitance, it represents minority carrier storage in the base region. So here you see we have C-Pi capacitor, that is diffusion capacitance. It represents minority carrier storage which is there in base region, and it is also there in terms of few picofarad only, right? Now if you observe resistance over here, right? So here we have RB resistance. See this RB resistance, that is there due to base contact over here. So because of base contact, we have RB resistance, and value of RB resistance, that is very small. You can replace this resistance by short circuit even, right? As value of RB, that is very small. See this R-Pi resistance, that is terminal resistance in between base and emitter. You see here we have base terminal, here we have emitter terminal. So R-Pi, that is a terminal resistance in between base and emitter, right? And value of R-Pi, that is 1 plus beta RD. See in my last video, I have explained you diode forward bias resistance, or you can say diode dynamic resistance RD, right? You see in my last video, I have explained diode resistance RD, right? And that is having how much resistance? RD into 1 plus beta, right? So RD value, that even I have derived. You see RD is 26 millivoltage by IE, right? And here resistance in between base emitter, that is RD into 1 plus beta, that even I have derived. So here see this R-Pi, that is resistance in between base and emitter only. So that's why here notation is different. R-Pi is how much? 1 plus beta into RD. Here I'm not going to derive this equation. That I have already derived in my last video based on RE model of BJT. So here I'm directly writing this, right? This R-Pi, that is 1 plus beta into RD. See this RU resistance, that is terminal resistance in between base and collector, right? This RU resistance, that is terminal resistance in between base and collector, and its value is large. Why its value is large? The reason is collector base junction is there in reverse bias. So collector base junction over here, that is there in reverse bias, because of which this RU value, that is very large, right? See this RO, that is resistance between collector and emitter terminal, and it is also very large. See in between collector and emitter, we are having two back-to-back diodes. Here we have collector, this is base, and this is emitter. So if you observe structure, over here, then in structure, you can observe, see this is N, this is P, and this is N. So here we have diode like this, you see. Here we have diode like this. So we have two back-to-back diode. This diode, that is there because of collector base junction, and this diode, that is there because of emitter base junction. Here we are talking about AC analysis. So this BJT should be there in active mode. In active mode, this diode that will come in forward bias, and this diode that will come in reverse bias. So in between collector and emitter, one diode is there in reverse bias. That's why resistance between collector and emitter will be very large, right? So R0, that is also very large over here, right? So these are the parameters which we have. In this, we already have another parameter like GMVB, that even I'll be going to explain you in this video itself, right? First of all, see this current source over here, that is having value GMVBE. So this current source is depending on base emitter voltage, right? This current source, that is dependent on base emitter voltage, and this GM is transconductance, right? So with high frequency hybrid Pi model, there are two versions. One version is VCCS, voltage controlled current source hybrid Pi model. So in which this current source is GMVBE, and second version is CCCS, current controlled current source, where you see this current source, that is beta IB. So there are two versions of hybrid pi model with high frequency. One is based on current source as per voltage controlled current source, right, where this current source value is VB into GM. And second is CCCS, where this current source is controlled by current, right, IB. So that is CCCS, current control current source, that is beta IB over here, right. That is how two different models are there. Generally we use this model, right, but there can be another version of it also, right. Now see, in this I have not discussed about what is GM, so let us discuss about it. See, GM is transconductance. So let me derive value of GM. See, GM is transconductance. So what is transconductance? See, transconductance is output current divided by input voltage, where output voltage is 0. So what is output current over here? You see, output current is IC, input voltage is VBE, right? So here you can say output current is IC, input voltage is VBE, right, where output voltage is 0. What is output voltage over here? Output voltage is VCE. So VCE, that is 0 over here, right. So one should know, see, this is IC by VBE, right. What is VBE? VBE is thermal voltage, right. And see here, if I say it is VT, then value of VT that one should know, that is 26 millivoltage, right. That is 26 millivoltage. Here see, IC by 26 millivoltage, that relation that I have explained in my last video as well. If you have seen that video based on RE model, so in that I have derived, see, this RD, that is VT by ID, where VD is 26 milli and ID was IE, right. So RD, that was 26 milli divided by IE. Let me take it over here. See, we have RD, right, we have RD, that is 26 milli voltage divided by IE. IE and IC value both are almost same, right. One should know this. IE, that is equals to almost IE, right. So as both are almost equal, you can say RD value, that is 26 milli divided by IC, right. So here you can observe this. See, GM, now that one can say 1 by RD over here, where RD is what? Dynamic resistance of diode in forward bias, right. So that is what I have explained in my last video, so I'm directly taking it from like last video, right. So GM, transconductance, that is 1 by RD. Here if you observe, see, we have R pi resistor. So R pi, that even I have told you, that is 1 plus beta RD. That is also coming based on last video, in which I have explained in between base and emitter, that resistance, that is RD into 1 plus beta, right, if current passing through, that is IB. So here see, value of R pi, that I have explained, that is as per R pi is equals to 1 plus beta into RD, right. And you see, RD, that is 1 by GM, RD, that is 1 by GM, so you can place it over here, and 1 plus beta, that is almost equivalent to beta. Beta value is there in terms of 50, 100, so 50 plus 1, that is 51. So percentage wise, you can say 1 plus beta is beta only, right. And see, this RD, that is 1 by GM, that one can say, so you can say R pi, that is beta by GM, right. And based on this, one essential relation that even you can remember, beta is equals to R pi into GM, right. And here one more resistance that we have, that is RO. Usually its value is very high. It is there in terms of mega ohm only, right. But sometimes they may give you data of RO in terms of H parameter, right? So one should know what is RO. See, RO based on H parameter, that is 1 divided by HOE. See, HOE means what? O means output admittance. E means common emitter configuration. So HOE means output admittance in common emitter configuration. So H parameter for output admittance in common emitter configuration, that is HOE, 1 by HOE, that is RO. That is how we have these parameters, right? So this is what about this high frequency model. Now I think we have discussed about all the parameters. So now I'm going to explain you low frequency hybrid Pi model of BJT, and that is what I'm going to draw based on high frequency hybrid Pi model. So high frequency hybrid Pi model that I have explained already, right? Now let us have low frequency hybrid Pi model. So first of all, what I'm going to do is I'll be going to consider terminals. You can observe this is base terminal, this is emitter terminal, right? And see here in between base and emitter we have voltage VBE, and here we have current, here we have current IB, right? Here we have current IB. Now see this RB resistance, RB is contact resistance at base. That value is very low. As it is very low, in low frequency one can do short circuit of it. So here I'm just doing short circuiting of it. So I'm not going to consider that resistance, right? This is short circuit. Now after that, you see here we have RPi. RPi derivation that we have already done, right? So here I'm going to connect RPi resistance, right? So here I'm going to connect RPi resistance, you see. And what is RPi value? RPi value, that is beta RD, or you can say 1 plus beta RD, right? So here I'm writing that 1 plus beta RD, right? That is RPi. Now if you observe here, see this CPi value. So CPi, that is happening because of diffusion capacitance, you see. And this diffusion capacitance, that is happening because of minority carrier storage, and it is there in terms of few picofarad. And one should know capacitance is what? Capacitance is having impedance, that is 1 by 2 pi fc, 1 divided by picofarad. So 1 divided by picofarad, that is a humongous value. If it is humongous value, you can provide open circuit over here. So this CPi, that is open circuit in terms of impedance. It is having huge impedance. So I'm not going to connect this. See this Cu, that is also there in terms of picofarad. So this value in terms of impedance will be very high as per Xc is equals to 1 by 2 pi Fc. So this is also open circuit, right? And I have told you Ru, that is capacitance in between base and collector terminal, and collector base junction, that is there in reverse bias. So you can say this value is also high. So Ru, Cu and CPi, that is getting open circuited over here, right? So as it is open circuit, I don't need to connect this. So I'm not going to connect this. So this is my input side. At output side, I just need to structure this only, right? So you see here we have collector terminal, here we have emitter terminal, voltage is plus minus VCE, right? Here current is IC, and you see here we have current source, that is happening in this direction, which is GMVBE, right? And this is what as per VCCS, where current source is GMVBE. If you have CCCS, then current source will be beta IB, right? So as per VCCS, I'm having this, right? For CCCS, it will be beta IB over here. And you see this RO, that even I'm connecting over here. That value is also high, but still you can connect it. Higher value in parallel doesn't make any difference, right? So that is how basic equivalent model that we have for low frequency analysis with the use of hybrid Pi model. So this is hybrid Pi model for low frequency, right? So that is how one can have this. Still, if anything that you would like to share, please note it down in comment section. I'll be happy to help you. Thank you so much for watching this video.